All right, so let's get started. Welcome to Lab 3. We're going to be focusing on vector and matrix multiplication here. Has everyone managed to pull the lab fully from Illumidesk? Any problems with that? Okay, good. So, brief reminder of vector and matrix multiplication. You have an n by k matrix here. You multiply it by a k by m matrix, and your resulting matrix is n by m. So the resultant matrix has the same number of rows as the first matrix, the same number of columns as the second matrix. This also gives you a hint that the order of your matrix multiplication matters. So a times b does not equal b times a, much to the detriment of some of my homework assignments last year. So our first example here, we have the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. The matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We're going to multiply them together and see the size computed using the Julia size function. So you can see here, the size function returns a tuple. The first element of the tuple is 3. That's the number of rows in our resultant matrix. The second element of the tuple is 5. That's the number of columns in our resultant matrix. Now, the second rule you have to remember is that you have to have the same number of columns in the first matrix as rows in the second. When that is not the case, bad things happen. You'll have a dimensional mismatch. This is what the error code will look like in Julia. It'll give you the dimensions of the first matrix, the dimensions of the second matrix, and tell you that those dimensions do not allow for matrix multiplication. So you have to rethink exactly how you ended up with those matrices. So to practice that, we'll move on to problem 1. So for problem 1, just make matrix 1 and make matrix 2. They can have any contents, so this might be a good opportunity to practice some of those special matrix making commands you've learned. But they must multiply together to form a 3 by 4 matrix. So a little bit of practice here for that resultant size. So just do that real quick. Give you a couple minutes.
We'll give you time to type in your... You'll spend more time dreaming what the numbers should be than the size of the matrix, okay? You have questions? Let us know. You can have trivia here to make sure that everything goes well. No problem?
Yep.
Okay. Magic numbers go. Find out. What do you call it? 3. Row. 4. 3. 3. Yeah. There's my reminder.
Does that say reminder? I always thought it said niner.
Reminder. That's my phone going. Reminder.
All right, anyone need more time on that? Cool. So for me, I'm just going to make a matrix with random numbers.
Did you declare that you're using the random command someplace?
Oh yeah. Or at least I assume so. Seems like it worked. And as you see, they're multiplied together to form mat product 1a And lo and behold, a 3 by 4 matrix full of completely random numbers. Now, your homework 3 is going to have these kinds of autograder cells. You won't be able to see the tests, obviously, but we're putting in more test cells where they're going to be public tests. So in this case, it's a rather direct test. We literally check to see, is the size correct? In the homework, though, it'll be more indirect tests. We might check to see if the sum of the matrix is correct. We might check to see if matrices orthogonal to it are correct. So the long and short, if you find the correct answer, the test will probably pass. The test will pass. But if your answer is incorrect, the test will fail, but it will not tell you exactly why they failed. So that's on you to figure out. We'll skip past this a little bit, just a little bit of more matrix multiplication resultant size practice here. So if you want more practice, you can do that on your own. And we're going to work a little bit on some clever indexing. So you already know that the colon operator pulls whole rows and columns from a matrix, which is pretty useful. Now, if you multiply 2 matrices, A and B, to create C, where A is this whole matrix and B is that whole matrix, you should extract the first and last rows of C and the first and last columns of C. So a little bit more matrix multiplication and indexing practice here for you. And then store those in top row, bot row, left call, and right call. Give you a few minutes to work that out.
Yep, and when you extract the rows, remember Julia prefers columns unless you're very careful.
Mm-hmm. Yep.
I could be wrong, but I think that you have a parenthesis here where the end parenthesis is supposed to hit top, so it's supposed to go sum, open parenthesis, top row, close parenthesis, equals 659, because I was getting a saying I was using Boolean in a spot I wasn't supposed to be using it in the assert.
Repeat the question.
No, I heard it. I messed up my little parentheses here.
So the question, yep, the tests.
Good catch on that one.
You're excused from lab. And you will replace John 2 weeks from now.
Yep. Thunderdome style IA assignment.
Yeah, so remember to help the people on Zoom.
Yep.
But also, when there are questions in class, let's try to have me bring the mic or you repeat them. Yeah, but
Definitely. Okay, I'll give you 1 more minute for that. All right. So you see here, top row is extracted with the first row.
is it extracted as a row?
Let's find out, shall we? Extract as a vector. So not as a specific row matrix. Although, for most intents and purposes, Julia is smart enough to be able to use that vector for ostensibly matrix operations. For example, you can take the sum of a vector, and you can also perform matrix multiplication with a vector. It's just that if you really, really, really need a row vector, this will not give you that. In order to get that row vector, I believe you do this, right? And now we have a 1 by 4 matrix. Yeah, wait, hold on. When to use brackets and when to use parentheses, definitely. So Julia does things different than MATLAB, but perhaps more similarly to programming languages that you may be used to. So brackets are used for indexing. If you want to access a member at a specific position in a matrix, you use brackets. Parentheses are used to pass arguments. So if I have a function, like for example, sum or println, then you wrap the arguments, which are everything in the middle here, in parentheses. And if you actually see, Julia is able to identify that you're giving it a function when you put in those parentheses. That's how it knows, oh, okay, clearly sum is the name of some function, so I better look for that.
Yeah, for all you MATLAB programmers out there, if you're like me, it's a nightmare at first because you just want to go open parentheses when you're getting the entries from a matrix. It's just a reflex, okay? You can't help it. You just can't help it.
So, and then here is a handy trick for just calculating the size on the fly. By passing it 1 as an argument as well, you remember before that size returned actually a tuple. It returned 2 values for the dimensions of the matrix, 3 and 5. And the first value is the number of rows, the second value is the number of columns. So, lo and behold, if I can find the place I was at, if I say size c, 1, it'll say, he only wants to see the first value of the tuple, so it'll only give me the number of rows. Similarly, size c2 will only give me the number of columns, the second value in the tuple. So this is helpful if you're doing some inline commands like this, just to make your code a little tighter, a little more readable maybe. But it'd be equally valid to pre-declare what the rows and columns were and do it like that. So we run the autograder test. We see that everything is nothing. So we're happy. This is also, by the way, the form that your homework autograder test will probably look like. It's not going to directly test the value of the columns. It'll test the sums. So now we're going to start building up into you making your own function to perform matrix multiplication. So we're going to give you these 2 relatively small matrices, F, yep.
Sorry, do you want to just quickly going back for I just wanted to see the column again, what you did for the size.
Sure.
All right, so just 1 indicates doing a row and then 2 indicates a column.
Yeah. Or 1 indicate, yeah.
Sorry, that's the problem with math and a deaf professor.
Should I just repeat it?
Yeah, go for it.
I was just asking the difference between, when using the size function, having a C and then the second parameter being 1 returns a row and then 2 returns a column.
Yep.
Okay.
And the easiest way to remember that is that if I just call size C, it gives me 2 values. The first value is the rows, and the second value is the columns. So.
Oh, right. Sorry. I'm just so used to indexing from 0. It's confusing. So.
I hear ya.
Yeah. Okay. Thank you.
Yeah.
I think we just found a C++ programmer. Am I right? Oh, with our indirect test, John, and we didn't have to ask him. We just said, how do you index?
Fell for our trap.
So that's one of the other things. If you have other programming languages that are 0 index versus MATLAB and Julia that are 1 index. So the first entry in an array is the 1. In C++ or C, it's 0. Python, it's 0.
Yep.
Now, John, instead of putting the size, if you'd have used the end command, would that have worked fine too?
I'm not as familiar with the end command.
Yeah, so why don't you try it? Replace the size and just use end, and not with C comma 1, just end. It should take the last index.
You're saying just like that?
Yeah, and give it a whirl, run the test.
Oh, you're watching a little bit of magic happen there, folks.
So that's another shortcut, okay? So John was trying to emphasize, if you want to get the size of a matrix, you've got it, you get the rows and columns. But in MATLAB and in Julia, end takes you to the last index in either in the row or the column. So it's just a little shortcut as well.
So we're going to start now building up towards you making your own matrix multiplication function. So we'll start that off by multiplying the matrices F and G by hand, by partitioning F into rows, G into columns, and computing the product using row by column matrix multiplication, as is shown above here. And this is the lengthy form of matrix multiplication, so don't worry, we'll be automating it in just a second.
Just trying to understand here, do we really know what's under the hood of matrix multiplication? Need to be indexing into the matrix. Range F. I think you need F. Here's the other secret of teaching. Look on the stage, your IQ drops. Just exchanging a little wisdom with John that when he's on the stage, his IQ drops by about 30 points. It's a well-known effect of having to have a mic strapped to you.
You should declare F and G first. I just threw it in here because I was too lazy to do that currently. So, but I'll do it at the end. Okay, I'll give you a few more minutes to finish that. So we have a question in chat. Why did you do fr1 is equal to f1 to 1, comma, colon? So the reason we did that is, as Professor Grizzle pointed out earlier, this is the proper way to extract an actual row matrix. So I was trying to be a little bit cheeky, a little bit lazy, and just work with the vector, which will work. But the proper way to do it is to just extract the row, which is what this does. It tells Julia, we know that you want to give us back a vector, but we want a row matrix. It's a little bit of a cheeky workaround, because if I did, for example, 1 colon 2, as you'd expect, it would extract 2 rows. and then it would actually be a matrix, right? There's no way to represent a 2 by 2 matrix as a vector, right? So this then is a little workaround in order to always return a row matrix. Wouldn't it be simpler to just say F1 comma colon? So if I do that, you'll see that it returns a vector, not a matrix. But if I put in the colon here, now it actually returns a row matrix. Yeah. Oh.
See, I knew you were going to want the mic.
If that is an issue that it's going to create a column vector, can't we just add an apostrophe at the end? Like 2 characters versus 1 character, but.
So if we do that, you'll see that you get an adjoint, which is a wonderful data type, which I don't honestly know exactly what it does. It simulates a row vector. It's useful for, I know it's useful for higher degrees of math, many degrees higher than the math we'll be doing in this class. So it's represented as a sort of row vector, yeah, but it's really, it's potato potato. It'll be treated like a row vector.
Gotcha.
So you even see that it realizes it's a 1 by 2 adjoint. So it's really whatever you feel. This is how I did it last year, was I would just put an apostrophe at the end.
Both are fine. If you get up into math and you do vector spaces and you do dual spaces and you take elements, so the adjoint of a linear operator acts on the dual vectors, but the main thing is the adjoint times a column vector is always a scalar. For us, the adjoint is a row vector. It's the same thing. So it doesn't matter which one. You'll see in our solutions, we have both often. We use both, go back and forth. Is it a good thing that Julia is so focused on column vectors? I'm not sure, but that's how it goes. Yep.
I got thrown an error when I was trying to compile this. It says no method matching star and a lot of weird stuff. Did you get that too?
Let me run over there real quick.
Well, that's because you didn't do the 1-to-1 and the 2.
Oh, so that's necessary?
You got the same thing? Oh, let's take a look
Yeah,
at this.
see, if you take 2 column vectors that are 2, 1, so it's 2 rows and 1 column, cannot multiply another column vector that is 2 rows and 1 column. So you will get an error. So
I did the 1, 4, and 1.
yeah, the error we had in class is, John was about to do the same thing, and I saved him.
Pretty sure that's
you're
a 3.
not indexing. You're indexing into nothing if you don't have the F there, and then you put the F back, and you're indexing into the matrix. Just a typo, a braino, okay? So. Mm-hmm.
So, yeah, this is back on. So we had 2 really good questions. Up here, because I was trying to keep you on your toes, you actually have to adjust the sums. So the sums are declared wrong here. So you should move the equals, 659, 1355, etc. Should move those outside the parentheses. They're not supposed to be inside there. Because what's the size of a Boolean? Who knows? The second question we had was down here. And we had a few interesting errors going on. So when you're declaring it, you should delineate the different matrix elements with spaces and not commas. Otherwise, Julia apparently can get annoyed, or at the very least, not really understand what's going on. So when you're declaring your matrix, just separate the elements with spaces and not columns like that. Otherwise, it may get confused and break for no obvious reason, but regardless.
Because it's not MATLAB? Yeah, MATLAB spaces and commas are the same. Julia semicolons and commas are the same.
Yep.
So once again, these languages are too close initially, and yeah, I fell into all those pits, so I feel for you guys.
I also had that error. Yeah, if you could put in the chat which error that was, then I'd be happy to go over that. And just for people who can't see the board too clearly, these here are semicolons and not colons. The semicolons are what marks the start of a new row, whereas a colon will construct a range of numbers between the first number and the second number, which is obviously not what you want when you want a 2x2 matrix. So now it's time for the fun part of the lab. You're given two matrices, C and D. These ones would be very annoying to compute by hand using the method that we just used. So we're going to use a nested for loop. And you should fix the loop indices for the for loop. And then put your code in the middle of the inner for loop. Or you can put your code wherever in the for loops if it works, but it's suggested you put the code in the middle of the inner for loop. I'll give you a bit of time to do this because it can take a little bit. Yeah.
I just have like a, I guess a Julia question.
Sure.
So it got to the point.
Helping all the online people.
So, I mean, I guess I'm just used to C++ coding and things like that, but like for product 2B, when you're doing the open square bracket I comma j, when I was doing it, I was doing open I close, open j close, just because that's how like normal 2D indexing works. Is there a reason why that doesn't work with Julia, or is it just a Julia thing? Like,
Have you seen that doesn't work with Julia?
I tried doing it and I got a really strange error saying like float. It's saying a type mismatch. I don't remember exactly what it was.
I know what you mean. So what Julia is trying to do is Julia, like C and C++, supports multi-dimensional arrays in the sense that programming understands. So, for example, you can make a matrix of matrices, or you can make a matrix of tuples. So what it's trying to do when you feed into it, product 2B, open brackets I, close brackets, open brackets J, close brackets, is it saying, well, okay, let's look at the first element, or let's look at the ith element of product 2B, and the jth element of that element, but it's an integer, and the integer only has one element? What's going on here?
Okay. Gotcha, that makes sense.
Yeah.
Thank you.
I believe there will come a time when you are going to use that multidimensional functionality, so don't curse it too much, even though I know it's annoying.
I swear my code is right. There's just a very strange error.
I hear you. Yeah.
What does I'm not sure what the size function does, I guess, because what I'm used to, I guess, in MATLAB and C++ is just like you put in the size of a list. Well, maybe that's what I'm thinking about, but
Yeah, I think it's doing what you think it's doing. So what this is going to give me is it's going to set n equal to the size, to the number of rows in matrix C. And then likewise, it's going to set m equal to the number of columns in matrix D.
so the 1 and 2 represents 1 for row, 2 for column.
1 for row, 2 for columns.
Gotcha, thank you.
How are we doing online? Any questions?
Seems like we're okay so far.
Yeah, for the first couple of weeks, all of September probably, we'll be struggling with those who know some MATLAB, trying to convert that to Julia knowledge, and it'll be like those who have taken Spanish and now you're learning French or Italian. There's so many false friends between the two languages. It drives you crazy at first, and then it becomes second nature. Rows, columns. Okay, I can handle this, John. I've got this one figured out. You're showing your C lineage. You're in 281 now?
Yep.
Yeah, that's a problem. That's your problem, okay? Me, I'm kind of a dummy. I don't know. So all we need is the, I'm not very good with your keyboard here, so. Can you get me over here and just get me the single J? Whoops, that's not what I wanted to do.
Just one J?
Just one J? Okay, now, here's the thing. This is a matrix when I extract the row on the left. And this is a 1 by M, 1 by K, let's see, K is 3 here, 3, so 1 by K matrix times D, that is a K by M, which is 3 matrix. And the product of two matrices is a matrix. Now Julia, even though that product is a 1 by 1, it's a 1 by 1 matrix, and we're trying to put that matrix as a scalar into this product 2b, okay? So here, I would write that as 2 lines, but you can do it as 1. So just do parentheses around those two things.
Some.
No, and extract from that matrix the scalar. Outside of it, bracket, 1. No, 1. There's only one entry there. It's a 1 by 1 matrix. Now run your code. The old guy knows something, okay? So I'm always floored. So this is all of the typing of Julia, okay? So if you run into these errors, it will be often because you've got a 1 by 1 and you're treating it as a scalar. So let you get here. I want to go back up to where John did something similar and just stack them up, and he did not generate an error, and let's talk about why that worked. Okay, so let people copy this down. Or why don't you copy this and stick it into chat for those who are online really quick. this cell. Yeah, just stick it in the chat. You get your mouse over there. You're doing, almost got it. It may be over here.
They're shared like that.
Huh?
I don't think they're shared like that.
They are. Oh, it's not.
it's
You're
being
right.
used as an
You would have to
external
log on. Yeah, you can't do that. Okay, that's a bummer. Okay. That's a good idea. So it's a matrix. It's a matrix. Okay, now let's go back up several cells, John, where you just took the product and stacked them up and see why that was not an issue, like here, right here, okay? Show FR1 times GC1. That's going to be a 1-by-1 matrix, but you can stack up matrices and build other matrices, and it's still the matrix type. Okay, so show that, yeah. And show the other one just to make it super redundantly, awesomely clear, okay? So FR1 times GC1 was a 1-by-1 matrix, okay, that's fine. Now let's take F and G. F has 2 rows and 2 columns, and G has 2 rows and 1 column. Let's form a matrix H, which is F space G, just for the fun of it, and just show you how you can. So now these matrices have the same number of rows, so I can use them as columns, okay, of another matrix, and show H. And everything is cool. So you can take matrices and build matrices. So that's the type issue. Julia knows what a matrix is. And when they have the correct size, you can either stack them up into columns or you can stack them up into rows. So here we stacked F and G as columns and built another matrix H. And since this product, we had a 1-by-1 matrix stacked on top of a 1-by-1 matrix, so use your mouse and highlight those because my finger is not doing a very good job. So that's a 1-by-1 matrix, FR1 times GC1s, and then underneath it, another 1-by-1 matrix, and that gives us a 2-by-1 matrix. So that's why that one worked, okay? Super.
So here's a fun trivia question for you. You'll see that when I return this, it's of a float data type, or it's of a non-matrix data type. Probably this would categorize it as an int. But down here, I could not assign this, which would give us a 1-by-1 matrix, to that. Now, does anyone have any idea why that would be, and why Julia kind of got freaked out when I tried to do that? Oh.
Because you're setting it to default zeros, which is expecting a bunch of scalars, and when you were passing it was just a matrix of a 1-by-1.
That's exactly correct.
So repeat that answer.
So the answer given.
No,
Okay.
you were given. He already had declared that the product up here in row 4 consisted of real numbers in its entries 1, 2, 3, and 4, okay? So
Yep.
because zeros, those are numbers, they're not matrices. It wasn't a 2-by-2 matrix of 1-by-1 matrix. It was a 2-by-2 matrix consisting of 0, 0, 0, 0. And so it's expecting numbers to go into the IJ component there.
Yep.
And that's what has to happen. So
That's exactly right.
So when you see these types of errors, think about types, use the show command to print out intermediate things. When you see your numbers within brackets, that's a 1-by-1 matrix and it's not a scalar. So these are, to me, it's kind of annoying. I'm sure it's very important for other things to get your types perfectly correct, okay? But that's part of where Julia is.
So we have a question in the chat. In the for loop, why is product 2b I comma j? Why is the I comma j there? So the I comma j is there because we're building up the product matrix element by element. So we already know that it will have n rows because C has n rows. And we know that it'll have m columns because D has m columns. So we iterate through 1 to n, we iterate through 1 to m, and what we get essentially is the full set of the coordinates of product 2b. So you'll have 1, 1, 1, 2, 2, 1, 2, 2, etc.
Yeah, it's the ij entries in the matrix.
Yep.
Because no one ever uses j for the rows and i's for the column. It's ij, okay? It's just the way it is.
Then if you go over line 11, why it has 1 at the end / what it does. So what this 1 at the end does is, I'll even put back in this show command here. So as my mistake earlier showed, what Julia does is it calculates, okay, I'm multiplying matrices, the result is a matrix. It doesn't matter how nonsensical it is that a 1-by-1 matrix is strictly referred to as a matrix. It's going to refer to it as a matrix. So what we have now is a 1-by-1 matrix, but we're trying to assign this into our product matrix. And our product matrix, we already told Julia, is full of floats or integers or some other data type that Julia is smart enough to be able to convert between. So we try and assign a matrix into an integer. And it doesn't matter that it's a 1-by-1 matrix and that really it should just count. It doesn't even look that far. It just says you're trying to assign a matrix to an integer. That's not allowed. So what this 1 does is we have a 1-element vector. So we access the first element of the 1-element vector in order to get that value, which is an integer. And then we just assign that to the product 2b at the correct ij coordinate.
Yeah, so go back to lab 1 and look at the example small matrix. You're given a small matrix that had 1 entry, and then we extracted the number out of that 1-by-1 matrix. So go back to lab 1.
Yeah.
We've got about 5 minutes, and then we're going to be at 5:20. So
Yeah.
let's do the,
function. So
let's
just
skip this, let's
okay.
skip this. Let's go to building a function.
Well, that's
Oh, that is that,
Yeah.
okay.
So you'll see that the script that you built here, it's a little
Maybe
bit.
I'll take it from here.
Oh, sure.
Yeah, but I might need you to manipulate the laptop. So I'll efficiently guide us through. So, okay, so obviously, you know, writing double for loops to do matrix multiplication is kind of stupid, right? You would never do that. You just do A star B, okay? Obviously. What we're doing is A, just getting through all of the syntax stuff on Julia to make sure we got rows and columns and understand that matrix times a matrix is a matrix, and even if it's 1-by-1, we have to extract out elements. So we're just kind of pounding that in. Now we're going to show you, though, with this simple example, how you build your own function. So this is when you're extending the programming language. It's not just sine there, it's not just cosine there, it's not the inverse function that's there. You're building your own function, and we're going to call it matrix product, okay? So, John, how do you have a touch screen? So can I scroll this down? Oh, no. Yeah, so I don't know. Okay, so we're going to, here's the syntax for building a function. You first declare function, it's a keyword, and it should always end with end, just like for loops have to end with an end, just like when we do if statements, they have to end with a keyword end. So function and end, those are really important. The other thing that's really important is you need the keyword return at the end, and you list what all of the values you want your function to return. So anything that you calculate inside of here, so you could be returning the rows, columns, temps, anything you compute here, you can then return as a function. So John, because we're running out of time, I'm going to ask you to just paste in from the multiply command into here and just build that as a function. Well, you want to take all of the fors and everything. Let's just take, yeah, the double for loop, paste it into the double for loop here. Okay, so we just encapsulated what you guys had, what was running in a cell, got our rows and columns correctly. Well, that's the other way to do it. Okay. Here, you can keep operating. I don't mind kneeling. I have no pride, okay? So, okay, so the keyword function, the keyword end, the keyword return, and he's going to return the matrix temp. So he's declared it. Now that Julia knows the size, we just initialized it to zeros. We'll show other ways to initialize them and then run the cell that will actually create the matrix. Now, if he wanted, he could do temp, comma, n, comma, m as well. So I want you to just put that in the return. You don't have to. Okay, so this is something the standard matrix command does not return. Okay, so now go ahead and run this. Now, it may be unhappy because you're returning not just the multiplication. Yep. Yeah, get rid of the show.
All right.
Because it's a bunch of random floats. I don't think this really already compare them nicely. Like, excuse me.
Just take norm of the difference. Or don't put the assert, just put function and then put minus c times d and just let people see it's 0, okay? Because we're running out of time here. Just get rid of all that. Get rid of the whole assert thing. Just return the answer. Yeah. And everything is 10 to the minus 16. Okay, so we're going to be using this in future homework. So you build functions and you can put anything in there, and we'll do LU factorization, we'll do back substitution, forward substitution, all of these methods. Okay, so let's scroll down, and you guys can play with the matrix reversal. It's just more exercises with functions. And post your questions in Piazza. You can build functions and use single for loops and double for loops. Let's do the wow, and then we'll take a break, okay? So let's run this cell.
I already ran it before because it takes a while.
Okay, so the Lorentz Attractor. You guys have heard of the butterfly effect? A butterfly flaps its wings in South America and it starts raining in North Dakota, okay? Because the weather is super sensitive. What that is a manifestation of what mathematicians today call chaos. What it means is a very small change in a value on an equation that models the weather can have huge changes in a further time when you're solving the equation on down. So the technical term is its extreme sensitivity of solutions of differential equations to their initial conditions. So what you can see here is this has two attractors. It stays around this point, and then it moves and it stays in a plane in this point, but you cannot predict when it's going to jump from one to the other. It's essentially random, okay? And so if you look at the code that's in here, it's showing you some of the really cool things you can do in terms of plotting and building functions. But this is the Lorentz Attractor is something you might see in a physics course. It was originally built as a 3-variable model of the weather to explain why the weather can never be predicted perfectly. And so what we're getting is if you take more and more and more and more and more local measurements, then you can make longer term forecasts and have them be accurate. But you can't just take the measurements in one place and predict them forward for long periods of time. And you can see here that, if you started here and you try to predict how many times it'll go round and round, you just can't do it. So you can generate random numbers by the time it takes it to flip from one cycle to the other. Just a little bit of science, the Lorentz Attractor. So Trivy, we'll take a 10-minute break and start the recitation.
Okay, introductions. I don't know how many of you guys know me, but I am Tribhi. I am the GSI for this course and also a PhD student in robotics. I was also the GSI last year, so hopefully I'm better this time. So the way I usually do this, I would go over whatever we have in our homework drill problems, have those laid out first. And then we open like a Julia section where we would probably just take up one of the last examples which people maybe struggle with. And we can go over it together, or you guys can code it, and that should essentially be enough for you to solve the homework problems. Or if you have questions on your homeworks, even before we get into it, that's always encouraged. And then if there's questions from the audience, we can just open it up and try to solve those questions together. So is everyone good with it? Yeah? Okay. Sounds great. So we didn't have a recitation last week because the hours we lost to Labor Day, and then we were just taking up extra questions. So most of this is going to be about homework 2, but if you think you're missing the background and you had trouble working on homework 1, I think the material's there, but I probably won't be able to cover all of it. I'll be taking up like 3 or 4 examples at most, and you would see that time just goes by like it's an hour. But we'll post the solutions online, and hopefully that should cover your questions. If it doesn't, bring it up, and we can do it in office hours. So we started out our course, and we talked about linear systems. And simply put, linear systems are just systems where you have no nonlinearities. Nonlinearities are basically stuff like if you see a cosine, a sine, or like square terms, cube terms in your equations, then your equations are no longer a linear system of equations. You're working with nonlinear system of equations, which means you're in the wrong course. The next part is we looked into solving these equations, and one way was to understand how to write these equations in matrix form. So instead of writing an equation as x plus 2y equals 6 and then solving it like you would in high school, we now write it as ax equals b, and then we try to find out if there is a unique solution or not. If there is a unique solution, we get down to solving it, or we'll see other methods of how we actually would have you guys do it. But for a good first test, we can use the determinant. So we get a system of equations like this, and we tell you to write it in the form of ax equals b. If you look at this, the way I break it down, and if you've been struggling with this, it should be helpful. Step 1, extract x. So from this, our x looks like it's going to be x and y, which is confusing, but that's the notation we're sticking with. Then step 2 is get the constants on the right-hand side and extract b. So your b in this case is 6 and 4. And then finally, Step 3, we extract our coefficients, which is matrix of coefficient, just a fancy term for saying the matrix A, which in this case, the coefficient of x in the first equation, 1, the coefficient of y in the first equation, 2, right here, the coefficient of x in the second equation, 2 again, right here, and the coefficient of y in the second equation, -1, here. Then we ask you, is the solution of this system of equations unique or not? Now, ordinarily, if you didn't use this method, you would get down to solving it, and if there was an inconsistency where you couldn't find an x and a y that was consistent, you'd say, okay, there isn't a unique solution. But because we know better now, we're going to use the concept that if ever the determinant is 0, the system may have either infinite or no solution, but if the determinant is non-zero, our system of equations has a unique solution. So if you look at this one, our determinant is 1 minus 1 minus 2 times 2. This becomes -1 minus 4, it's -5, which is not 0. And if you try solving it normally, you'll find that you'll be able to get a value of x and a value of y, which is unique and can solve, is consistent with your equations given here. And using the concept, and if you want to get practice on how to put stuff in, that's just me, okay. And if you want to try to practice how to put a system of equations into AX equals B, if you're struggling with that, try to do these problems or ask me now. Otherwise, I'm going to assume that you know how to do that. And that is pretty much essential moving forward. Right? We're good? Yeah. Otherwise, there's always, these are practice problems, work on them, and we will release answers tomorrow so you can work with them. So we know how to do that. We are going to forget how to solve it normally by taking equation 1, finding x, and then finding y. We are going to get a system of equations, put it in the AX equals B form, and then try to find the solution. Now, for the most general case of those, we don't really know how to do that just yet, but we'll go into that. I think with LU factorization, you'll learn a way to do it. But we already have covered how to do it for triangular matrices, where your matrix A is in a special form, where it can either be an upper triangular matrix or the lower triangular matrix. So if you remember, we covered in class where an upper triangular matrix is just a matrix where all the non-zero terms are above the main diagonal. This is the main diagonal, and above the main diagonal is the place where you'll find non-zero numbers, and everything below it is all zeros. Mathematically, if you look at the indices, you can say A of ij is 0 if I is less than j. And for upper triangular matrices, let's say I write this down as AX equals sum B, right? B here being a random vector of consonants, random vector of constants. So let's see, the equation would look something like 2x1 plus 3x2 plus 7x3, and then 2x2 plus 8x3, and then this one is 9x3 is some, let's say b1, b2, b3. So looking back to what we covered in class, what would be the method of solution? Do you remember going where we were like, okay, we'll solve for x3 first, and then we solve for x2 from the second equation. I don't know if we actually covered the formal name, but the method of solution would be called, oh, my bad, backward substitution. Is that something that sounds familiar? Something we've done in class, yeah? So every time you find a system of equations, you build an A matrix, and it turns out to be an upper triangular matrix, you know you want to use backward substitution because it falls into this triangle structure where it makes sense to solve from the last equation first and then keep substituting all the way up. And that's just called backward substitution. Similarly, for the lower triangular matrix, we don't need to guess, but this one's going to be forward substitution, right? We'll get the first equation, get x1, which would be easier, and then go on to the second equation, get x2, and so on. Is that clear? Am I going too fast? No, we're good. We get this forward substitution, backward substitution, everything's crystal clear. Because we're going to code this by the end of this class. Right? Yes?
Can you give a rundown on what backward and forward substitution is?
So we're giving a rundown on what forward and backward substitution is. So let's go to to forward substitution this time. So I said, whenever you see AX equals B, and you identify your A as being a lower triangular matrix, you should do something called forward substitution. What does that mean? So forward substitution means we're going to look at equation 1 first, solve for the variable x1. Then we're going to look at equation 2, take this value of x1, and it should just be the case that you're able to find x2 in terms of x1 from that equation. And then in equation 3, we already know x1 and x2 easily, and we're able to find x3 using the values of x1 and x2. So these are functions of x1 and x2. Let's see if that is actually true for a lower triangular matrix. So given my A is this, what I do is I'm going to write a random system of equations where that is the A matrix. And I'm going to assume this becomes 2 times x1 is equal to some constant b1. I don't know what b1 is just yet. Then 3 times x1 plus 2 times x2 equals b2. Then 7x1 plus 8x2 plus 9x3 equals b3. Does this make sense why we did that? Why does that become a system of equations that we're using here? Yeah? Yeah? So looking at this and considering we're going to use forward substitution, we look at equation 1. Is it easy to get x1 from here? It's pretty easy, right? You just get x1 equals some constant b1 by 2, right? Now, if I know x1 from the second equation, right here, is it easy to get x2? I think it is. Something like that. So you can argue, well, why do we need to call it formally like a forward substitution and go through all of this trouble when I can just look at 2x1 and just, it's easy to see, it's not, it's pretty intuitive. The reason we use this formulation is that you do want to end up coding it. So we want to look at patterns that can help us form it into a code. And we discussed a general form for a forward and backward substitution, where this is a lower triangular, and this is the general case of forward substitution. And this one would be the general case of backward substitution. And it's almost, so you see there's n computations, which means there's gives you an intuition. You have to write a loop that goes from 1 to n. And then everything on the right-hand side is known, so it's just like using a calculator, but doing a computation n times sequentially. So this is basically just giving us an idea on if I was given 100 system of equations with 100 unknowns, and there was, just by some magic, this special structure where the matrix of coefficients, or the matrix A, when you wrote it in that form, happened to be a triangular matrix, I know a code that can just solve it for me. Right? Does that make sense? That we're not going out of the way. This actually is a practical application. Yeah? Yeah. And you might argue that it's not general enough because not everything's going to be like a triangular matrix, right? That's too easy. But from what you'll see tomorrow is we'll go over LU factorization, where we can convert any matrix into this special format, where LU factorization is literally lower triangular, upper triangular factorization. So this is building up. This is like a building block. If you understand this, how to solve this, you'll be able to go. We're doing like a bottom-up approach. We're going to build up the basics, and then hopefully you can solve everything, and it's like magic, right? So does that make sense? Are we comfortable with first thing, getting a system of equations and building a AX equals B format? We're good with that, right? Then are we comfortable with recognizing what is an upper triangular matrix and what's a lower triangular matrix, right? That's good. And then do we also remember a special fact about triangular matrices, which comes in very handy, more than you think, where you know that the determinant of a triangular matrix is the product of the elements on its diagonal, right? If we're ready to remember that fact, it's going to come in handy, where we were looking at the uniqueness of a system of equations, right? In the beginning, we were like, okay, if the determinant of the matrix A is 0, then the system of equations does not have a unique solution. But if it is non-zero, then there is a unique solution. Now, with the triangular matrices, it's the same thing, but it's just gotten a lot easier, moving away from our general case. So if I ask you for this system of equations, you don't even need to probably write it down. Can you tell me if there is a non-zero solution? What would the determinant be? Determinant of A? Yeah, 4? Yep. And how do we know that? Well, we know that it looks like a triangular matrix. Let's try to put it in like A format, we see A is 2, coefficient of x1, and then coefficient of x2 from the first equation, another 2. Then the coefficient of x1 is 0 in this case, in the second equation, and you put that here. And then the coefficient of x2 from the second equation right here, just the 2. Doesn't even matter what your b is. We don't even care about it. It just matters what the determinant is, and that is enough to tell you if there's a unique solution or not. We recognize that it's actually an upper triangular matrix, and the determinant is the product of the terms in the diagonal, which is, it would have been better if it wasn't all 2's, but it's this 2 and this 2 that I'm multiplying. So it's 2 times 2 is 4, not 0 implies unique solution. We're convinced that it's useful when things are triangular. It's very easy to do things. We can just look at it and we're like, oh, I know the solution. I see a 0 in there in the diagonal. That one's a bust, right? Even if it's like 50 equations, somehow you can fit it in one page and you can track the diagonal. If you see a 0 in there, you're like, there's no unique solution to this one, right? How about for problem 3? What is the determinant? Does it have a unique solution? This is the problem I'm talking about. Yes?
Would be 800.
It would be what?
800.
Yes. 800. So we get, well, you should sometime, well, for this it's easy because I already arranged, but it's always good to see that this is x1, this is x2, x3, x4s. So it's not like they're jumbled up. Sometimes they are. But it so happens that it's already in like the right form. So you just multiply 2 times 5 is 10, 10 times 8 is 80, 80 times 10 is 800. Not equal to 0, unique solution. Didn't even have to solve it. Right? Now, are we comfortable doing forward substitution by hand? Yeah? Where we use the first equation, find x1. Is it helpful to go over it? Or do we just try coding it? Coding it is good? If anyone has, I won't get back to this. Okay. But we know how to do it, right? Naively, you would just solve this, take this x1, which will be 2, put it here, find the x2. I don't know the math for that, but you'll find something. Does anyone want to give me a solution? I have the answers. Yes?
X1 equals 2, x2 equals 4, x3 equals 6, and x4 equals 16.
Did anyone else get that solution? Should I check mine?
Or like without factors.
Uh-huh. Let me see. So 2, 4, 6. The last one's 8, according to me. I think you forgot to divide the 2, right? Yeah. So this would be 8. Okay, and remember this, and then when we code it, we should get the same solution, right? Should make sense. So before we start to code it, we have to kind of understand how to, we have to kind of recognize the pattern that we're going through, right? So for forward substitution, we always have a system of lower triangular matrix. Like the A is your lower triangular matrix. So your system of equation is going to look something like this. Is this form clear? So your A is A11, A12, A13, all the way to A1M. And here you go AN1, AN2, so on, all the way to ANM. So n rows, m columns. And then you open that up. There are n unknowns, so xn. And when you open it and write it in the most general form, this is what it looks like. Does that make sense? Or is it just unclear how these three things are fitting together? Making sense? Yeah? Okay. So we recognize that there is A11, but all these other terms are probably 0. So it looks like it's going to be a lower triangular matrix. Agreed? The system of equations, you see, it's going to be a lower triangular matrix. Yeah? And we know lower triangular matrix means forward substitution is the way to go. Okay. So we look at equation 1, and from here, you get x1 equals b11 by a11. And here we are assuming that a11 is not equal to 0. Trick question. Would we solve it if a11 was equal to 0? What would be the if statement you would look at? You're like, okay, we shouldn't even solve that kind of system of equation. What gives us that intuition? So we remember the determinant concept, right? So we know for a triangular matrix, first of all, the determinant is the product of all the diagonal elements. Yeah? Exactly. So because when we're solving AX equals B, the first check is you don't want to solve unless there isn't a unique solution, right? Because that is just going to confuse your computer. Your code doesn't work, it breaks. So to avoid your code from breaking, your first check should be that there is a system, the system is actually unique, like the solution's actually unique. And because we are working with a triangular matrix of coefficients, we know the easy way to do that is to just check that none of the elements on the diagonal are 0. Because if any of the elements in the diagonal are 0, that means the determinant is 0, which means there is no unique solution. Does that train of thought make sense? Does it come naturally? Yeah. So our assumption here that we've taken makes sense to everyone, where we assume that A11 is never 0. it will also blow up at x1. It'll be infinite. Wouldn't make much sense. So we get x1 is b1 by a11, normally solving an equation. Then for x2, take all the terms on except x2 to the right-hand side. So it becomes b2 minus a21 x1 divided by the coefficient a22, which is again not 0, and then so on. And the pattern we notice here is that let's do x3 again. So let's write x3. What would x3 be? It's kind of long. It'll be like b3 minus, can you guess just from the pattern? Take the general form, replace n equals 3 in here. What does that become? Yeah.
B3 minus A31 x1 minus A32 x2 divided by A33.
Amazing. So we look at looks like x1 goes to, the coefficient of x goes to everything below 3, and then you are multiplying it with the element in the third row and then the corresponding column. Looks like it'll make more sense when we actually start coding it, because it's, if you've seen homework 2, you've already probably solved it. Similarly, we can do backward substitution, where we start from the last equation, we find xn first, and then we make our way to x1. Right? If we're good with that, we're going to start coding it. Okay. Let me open the Lumi desk. Okay. I was gonna go over basics of Julia, but because we have a labs section, I think you guys should be competent. Okay, I'll skim over this, and you should tell me if any of these concepts have either not been covered in lab or you're having trouble with in Julia, right? So do we know how to use packages in Julia? Yeah? We don't have to add them. Illumidesk already has everything. So you don't have to get new packages. If you're trying to do a new package, you have to add that package, but that's not something you're going to need to do because we have it handled on the back end. You just say using plots, and then you're able to do plots. You know how to write comments, multi-line comments, right? Hash equal to. We have done homework 1, hopefully, so we know how to use math in Julia. If any of these are interesting to you, bring it up. I think they're pretty normal. I think one thing that's different is the integer divide. I don't know if you guys have done it, but it's just like, it just returns an integer. Nothing too special. If any of this looks interesting, bring it up. Something you've not seen before, something you want to know what it does. Then we know how to do comparisons. Yeah. Greater than, less than, not equal to, less than, equal to. I don't know if you've covered this. Have you guys covered this? How to actually use the help function in Julia. So anytime you want to know what something does, let's say you see a function in some notebook which is like rad to degree. Makes sense, it's probably like radians to degrees. But you just want to check the documentation. You put the question mark, space, name of the function, and Julia will tell you what it's doing. It'll give you an example. So rad to degree of pi in radians to degrees is 180 degrees is pi, right? So any function you feel like you don't know, just put it here and you should get your answer. Is that helpful, useful? Yeah? Okay, amazing. Variables in Julia, you know how to name variables. Hopefully you guys have covered this in class. Otherwise, go through this notebook. You might, if there's anything interesting, you might learn. You know how to display results, you know, using display, the difference between, what is the difference between print line and, yeah, sorry.
Oh, sorry, I just saw, like, as you were scrolling through, something I was wondering about earlier was just the semicolon. Like, I'm kind of, like, I see it in some cells and don't see it in others, which is like,
So when you're displaying stuff in Julia, if I run this cell, it's not going to do anything. Why? Because it's got a semicolon in the end. But if I remove that, it's going to show you a result. It's like MATLAB.
right, yeah.
Yeah. And it also really only does like the last line. So here, even if 1 + 2 gives an output, it's only going to print the last line, which is different from MATLAB. MATLAB will print out 3 and 7, right? But here it's like only the last statement will be printed out unless you put a semicolon on it, in which case nothing. And then you can use print line and display. They're both pretty similar, just like display is like this is just 3 and 7, but if you have like a big equation, you're using like symbolic variables, display is just gonna print it out in a much more beautiful way than the print line would. That's the only difference, really. And then this is relevant to only Julia. They have a lot of functions with like at stuff, like their macros. And that just shows you like x equals stuff like that. You'll see it all over your homeworks. It's usually helpful in seeing what's being printed out. And then we have strings in Julia. Hopefully you guys have covered it. You guys know how to concatenate strings. It's like just use commas. It's not like C where you have to have like this big string library and then you're trying to concatenate stuff. It's a mess. It's a lot easier in Julia. Vectors and matrices, you guys just covered it, so I'm not going to bore you with it again. But if any of this looks interesting again, stop me, right? We did this in homework 1. And we know how to index stuff, we know how to slice stuff. We went into it in depth in lab today. Was that helpful? In lab, do you have questions? I think you guys pretty much covered it. Okay. You can use stuff like maximum of an array and minimum of an array, which do, oh, I didn't define the array, but they do what you'd expect they do. They would give the maximum value and the minimum value. You guys know how to extract rows and columns? That was clear in class? Using either the apostrophe in the end or like the trick that John was referring to. No, okay. We're going to get back to triangular matrices. So starting with a simple example, because we already have it here, we wrote down x1 x2 is b2 minus a21 x1 by a22. We have these three formulas written down, right? So let's say it's only three equations, three variables. Does this make sense? We're given these three equations, right? First thing we do is we recognize A and B, and we fill them in. Is it clear why A is so-and-so and B is so-and-so? Yeah, we know how to put them. It's exactly like the drill problems. And then finally, we were using stuff like A11, B1. Does that make sense, how those would just be extracted as elements of a matrix? So A11 in this case would become B of 1, and divided by A11 is the first row, first column of the A matrix. It's the same formula written down, right? These formulas, we've seen them before. Yeah? Careful of the brackets here. You need the bracket. And then that becomes your x1, x2, x3, which is a column vector, x of 1, x of 2, x of 3. You're assigning those values in there. And we found them to be so-and-so value. I don't know. Well, what was the example we did? We did forward or backward? We solved for forward substitution. So we'll try to do that. So for x3, till x3, we wrote everything down. It was easy, right? But let's say I don't want to go through all of that trouble to go for x4. I want to just write my program down sequentially. How would you write it down in a loop? Do you guys want to try that for yourself? Does it make sense to do 2 loops, 1 loop? Is there a way to do this in 1 loop? Yeah? Do you want to elaborate? Do you want to elaborate? Why don't we need 2 loops?
You can do, I guess, I don't think it's not necessarily matrix multiplication, but it's the multiplication function. Where if you take, you can multiply one of the rows of A, so you can do the way that we have the slicing of matrix, where we take an entire row, just multiply that by x, and as we're filling in x, the zeros will multiply by 0, and kind of will ignore that part of it.
Yeah.
But the values that are there, we're going to start getting multiplied together.
So what you noticed was that we were working with triangular matrices, and we can use the special structure where stuff will automatically cancel out, right? So while it may, on first look, if you've been programming for a while and you're comfortable with nested loops, you'd be like, okay, one of the iterators is going 1, 2, 3, and the other iterator is going everything until I. It looks like a nested loop. But when you're doing coding, you want to use as little loops as possible. So if there is a way that you can avoid that and build a matrix formulation of it, that's the way to go. So how do we translate, is this making sense, the nested loop concept, all of that? How are you going to avoid it? I hope so. Yeah? Yeah? So I'm going to make a case that xn can be written as bn minus a of the nth. So let's do k. So n is the final, n is the number of rows you have. I'm going to say for any kth row, xk is bk minus ak comma, so basically the kth row of A times x divided by A k k. Does this make sense? Does it actually make sense? It really doesn't, because the size doesn't compute. I just wrote down x. What is x? If my x is, I don't really know x just yet. What should be initialized? Yeah.
Well, x should just be like 0 for now.
Yeah. Why?
Because,
So the answer was x should just be zeros for now.
because it, right now, I mean, I guess if you take, since there's nothing in it, and like starting, I guess, at the first value, it's just going to be b of 1 over a 1, 1. But then, like, once something gets, and then I guess something will be put into x, and then it's just like doing row, column, multiplication, and then it ends up just working out because it just does.
Yeah. No, you're right. So the answer was we need to initialize x equals 0, 0, all the way to this n zeros here. Oh, n cross 1. Why? Because, first of all, any row of A, what would be the dimension of this vector? A is n cross m, right? I'm asking you how many elements are there in one row of, oh, this is m. How many Hold on, I confused me. Oh, it's just transpose. Yeah. Right? Yeah, how many elements are there in a given row of A? M, right? So it's it is also m cross 1, which is why we will transpose it. So A has n rows, m columns. So for any row of A, how many elements are there? M, right? If I lost anyone, tell me now. Because this train is going full speed. We don't want to lose people. Yes? Emerald, nod for me. Twice if you understand. Thrice if you want to leave. Okay. So, and then we also know Julia does this dumb thing where you extract stuff from matrices and they're going to be columns. So this will be m cross 1. It's a column vector. And we realize x is also a column vector, which is for now zeros, right? So one of these needs to be transposed. Which would you do for this matrix multiplication to make sense? What should we transpose?
Wait, are they both, they're both column vectors right now?
They're both column right now. The first one, right? So if it's A times X, then I should be transposing, not like, it's not A, but like a row of A. So this becomes kth row extracted and then finally made it row in Julia again with the transpose times X, which is all zeros. Why is it all zeros? Because we want to be, if there is any basically, we don't see any A12, A13, A1M in this equation, do we? No, right? We want to be able to cancel those out. So if, this will make it easier. Hang in there. So if I write AX normally, it is A1, X1 plus A11, A12, X2, A1M, XM. If it wasn't triangular, this is what it would be, right? How do I translate this into the first equation right here? The easiest way is to make all of this 0. How do I make that 0? Well, my x is initialized as 0. So for the first one, for k equals 1, do we agree that this is going to be B1 by A11? Yeah, because of our initialization, that's going to fit in. Then for k equals 2, what would be x2? We're just using this form now and trying to see if it actually is what we want. X2 from that form becomes B2, right? B2 minus A of, A is all of this, right? And we're extracting the second row. So the second row, I write down A21, A22, A2M. I'm multiplying this with, now our x is updated, right? So x1 has something. x1 has x1. x1 is not 0 because we updated it. And these are all 0. What does this product look like? A times x will be A21 x1, right? Everything else is 0. There's only the first x1 that has a coefficient. So this whole thing becomes, it's a mess, but we're going to give you like type set solutions, so you'll be fine. This would be A21 x1 divided by this diagonal term, AKK, A22, right? So for k equals 2, we've proved that this form is equivalent to this form is equivalent to this system of equations. Does that make sense? Has that simplified our life or not? Yes? I can go over this again if that's helpful. Again? Yeah? Okay, we'll do it again. Let's do it with the example we had here. This forward substitution, right? Step 1, we write down x. What is x? Well, we're going to initialize it to be zeros. Step 2, write down your B matrix. 4, 28, 22, 46. Step 3, extract coefficients. A matrix. 2, 0, 0, 0, 8, 3, 0, 0, 2, 3, 1, 0, 2, 2, 3, 2.